Okay, this is part D of the 2015 question 4. If you haven't looked at the previous video on part C, have a look at that first because this one follows on from it. This again is dealing with Miner's rule. Previously we'd worked out the values of A and C having already been given the value of B. So what we have in this case is A, I'll use a value of -7, B we'd already got as -1000, and C I'll use a value of 4992. And what we need to do is remembering that we're dealing with Miner's rule, so that is the log of the time to failure is equal to A plus B over T log sigma, the stress, plus C over T, where T is the temperature in Kelvin. So what we've got in this particular question is we've got a pipe with a diameter of 20 centimeters, a wall thickness of 3 millimeters, pressurized with water as follows. So it has an initial pressure of 0.24 megapascals at 20 degrees C for 4 days. It then has a pressure of 0.3 megapascals at 50 degrees C for 1 day, and it then has a final situation of a pressure of 8.18 megapascals at T equals 30 until it fails. And what we need to do is to work out the overall lifetime. So what we need to do with this is to work out the proportion of lifetime that is used up in the first part and the proportion of lifetime that's used up in the second part, to then work out what the remaining lifetime is in the third part. So there's quite a few steps to this. For each of those parts we need to use Miner's rule to work out the time to failure, and then work out for the first part how much of the time to failure is 4 days, for the second part how much of that time to failure is 1 day, etc. The other thing that we need to note with this is that we've got pressures here and not stresses. Miner's rule works with stresses, so we need to convert our pressures to stress. So what we have for a pipe, the largest stress will be the hoop stress, so we need to get the equation for the hoop stress. It is in the formula sheet. I won't copy it across because it's fairly straightforward. It's just given by PR divided by T, where P is the pressure, R is the radius, and T is the thickness. So what we then need to do is for each of those parts work out the time to failure and the proportion of time to failure that we've used up. So if we do those one at a time, the first part we have we need to work out the pressure first, work out the stress first. The first part, the stress is the pressure, which is 0.24 megapascals, times the radius, which is 10 centimeters because the diameter is 20 centimeters, so 0.1 meters, and the thickness 3 times 10 to the minus 3. And if you work that out, that comes to be 8 megapascals. So what we then have is putting that into Miner's rule. So we have log of time to failure is A, which is -7, plus B, which is -1000, divided by T, 293, because we're dealing with 20 centigrade, times log of the stress in megapascals, which is 8, plus C, which is 4992, over T. Oops, 293. And if you work that out, that comes to 6.955. That's the log of TF, so therefore TF is 10 to that, which is 9.02 times 10 to the 6 seconds. So what we then have is, this is for 4 days. So 4 days is equal to 4 times 24 times 60 times 60, which is 3.456 times 10 to the 5 seconds. So therefore the fraction used, the fraction of the lifetime used, is the time 3.456 times 10 to the 5 divided by the lifetime under that condition, which is 9.02 times 10 to the 6, and that comes to equal 0.038. So basically that first exposure condition uses up just under 4% of the lifetime. We then do exactly the same for the second part, so it's a little bit repetitive, but go through it for the second part as well. So the second part, we have the log of time to failure here is equal to A, need to work out the stress first. Apologies about that again. So in this case the stress is 0.3 which is the pressure, times 0.1 10 centimeter radius divided by 3 times 10 to the minus 3 thickness, and that comes to be equal to 10 megapascals. So then we have log of time to failure is equal to A, which is minus 7, plus B, which is minus 1000, divided by the temperature, which is here 323, we're at 50 degrees C in this case, times log of 10, plus C, 4992 over T, which here is 50 degrees and 323. And if we work that lot out, that comes to 5.36, which means that the time to failure is equal to 2.29 times 10 to the 5 seconds. And what we have here is we have 1 day of exposure in this condition, so that's equal to 24 times 60 times 60 seconds, which is 86400 seconds. So therefore the fraction used is the time that it's been exposed at under that condition, which is 86400, divided by the lifetime under that condition, which is 2.29 times 10 to the 5, and that equals 0.378. So a bigger fraction here is used up almost 40% of its lifetime under this hotter, higher stress condition. So what we then need to do is we need to work out the lifetime under the third condition, and then the last bit is slightly different because we work out how much is left and what the lifetime under that condition will be. So again, for the third part, we need to work out the stress. I've remembered it this time. So the stress is the pressure, which is 0.18 megapascals, times the radius, 0.1, divided by the thickness, 3 times 10 to the minus 3, which is equal to 6 megapascals. And what we then have is the log of time to failure is minus A plus B, which is minus 1000, divided by the temperature here, we're at 303, 30 degrees, log of 6 as the stress, plus C, 4992, over the temperature, 303. And that lot equals 7.285. So the time to failure here is 1.927 times 10 to the 7 seconds. So what we need to look here is how much of our lifetime is left, what fraction is left. So fraction of lifetime left is equal to 1, the whole lifetime, minus the 2 bits that we've already used up. So under the first condition we used up 0.038, and under the second condition we used up 0.378. So we have 1 minus 0.038 from the first condition, minus 0.378 from the second condition, and that comes to 0.584. So then what we can do is we say the remaining lifetime under that third condition, so the remaining lifetime is equal to 0.584 times the time to failure under that condition, which is 1.927 times 10 to the 7, and that lot equals 1.125 times 10 to the 7 seconds. And if you work that out, that comes out to be 130.25 days. The other 2 bits are in days. The total lifetime, which is actually what the question is asking, the total lifetime is what we had: 4 days for the first condition, 1 day for the second condition, and 130.25 for the third condition, which is 135.25. That last bit is a little bit trivial, and I think you'd have only lost 1 mark if you'd missed that out. So the key parts to remember with this one is for each of the conditions that it's under, using the values of A, B and C, work out the lifetime that you've got under each condition, work out how much of the lifetime as a fraction has been used up by the time under that condition, and add up what's already been used up as fractions, work out what is left as a fraction, and then you can multiply that by the time to failure under the final condition to give you the total lifetime. And yes, just other things to remember: the stress should be in megapascals, temperature in Kelvin, and just make sure you do the calculations right and you'll be fine.